Hello everyone, my name is Giuseppe and I am a PhD researcher in information security at Royal Holloway, University of London. It's a great pleasure to be here and I hope that you will find my talk on serverless computing interesting. Most of you are already familiar with the serverless computing model, but to ensure that everyone is on the same page, let me start by briefly summarizing the main points. This model, also known as FaaS, Function as a Service, can be seen as an evolution of two consolidated cloud computing models, Infrastructure as a Service and Platform as a Service. The objective of this evolution is to provide developers with a platform that offers several cloud-based services and that is managed by a cloud provider, for example, Amazon. As a result of all this, developers can focus on the development of the business logic of their applications. These consist of functions, for example, implemented in Python, that interact with the cloud-based services such as AWS S3, a data storage solution, and AWS DynamoDB, a NoSQL database solution. These functions are also called handlers and are triggered by events of different types, for instance HTTP requests and database updates. So why has the FaaS model become so popular? The key advantage is that the cloud provider takes care of the infrastructure, including issues such as scalability and maintenance. However, securing serverless applications, as I will explain in the next slide, is a complex task. At this point, your question might be, in an environment managed by a cloud provider, what are the security risks that developers need to be aware of? The CSA, the Cloud Security Alliance, has already provided an answer to this question. And here you have the list of the 12 most critical risks for serverless applications. The list is a mixture of old concepts, for example injection attacks and broken authentication, and serverless specific risks such as financial resource exhaustion and cross-execution of data persistence. The key point is that even though some of these concepts are consolidated, serverless applications provide a new context which needs to be properly understood. In addition, there are indeed serverless specific scenarios. My favorite example is financial resource exhaustion, which happens when an attacker manages to repeatedly trigger workflows, and this implies that at some point an application might become unavailable because there is a large bill that someone has to pay. Considering all these risks, it is not surprising that cloud providers and security researchers have been working on innovative tools to secure these applications. And this is where our research comes in. In this paper on data flow analysis of the serverless applications, we explain how we are building a static analysis framework for these applications, and we propose a new suite of micro benchmarks used for its evaluation. All our micro benchmarks are implemented in Python, one of the most widely adopted languages in this area, and you can find them on GitHub. Considering the popularity of the serverless paradigm, it is not surprising that several serverless security tools are currently available. However, most of such tools rely on dynamic analysis. We don't aim at replacing them, but we believe that static analysis can effectively supplement these tools. And why is analyzing serverless applications statically challenging? First of all, it requires extracting information both from the infrastructure and the application code. The infrastructure code is where the necessary cloud resources are specified. In addition, serverless applications are typically stimulated by a variety of sources and events, and the code that implements the platform services is not available. There is an additional challenge, though. The majority of the existing benchmarks are focused on performance evaluation and cost effectiveness. For this reason, we have designed a new suite of security-oriented micro-benchmarks which were used to evaluate our approach to detecting security-sensitive data flows. To clarify in more practical terms what we've been trying to achieve, let's consider a motivating example. This simple application has a user control entry point, the HTTP post request, which triggers the execution of three Lambda handlers. The first is triggered by the HTTP post request itself. This handler then calls the API upload file, which raises an event and triggers the execution of the second handler. The API call putItem raises another event, and this is the reason why the third handler gets executed. The problem is that part of the information provided by the user in the HTTP post request is used in the last handler to execute a system command. This means that this application includes an event-triggered data flow that leads to code injection. The key observation here is that a general-purpose static analysis tool wouldn't be able to detect this vulnerability because it wouldn't consider the effect of the triggered events. This explains why we are working on a new static analysis framework to detect security-sensitive data flows. Our suite consists of 10 micro-benchmarks which were designed by considering two inputs. The first is a collection of vulnerabilities that lead to code injection information leakage. The second input is the characterization in terms of cloud services and APIs of the Awesome Pi dataset. The application visible on the top right corner is the motivating example that I have just described and is also one of our micro-benchmarks. The table on this slide shows that 7 micro-benchmarks are interprocedural. As for the included vulnerabilities, 7 micro-benchmarks are focused on code injection, whilst the others contain information leakage vulnerabilities. To explain a little bit better what our suite includes, let's consider another example. This is a micro-benchmark with an interprocedural data flow that can lead to information leakage. HTTP post request is the user-controlled entry point of the application. The request triggers the execution of a Lambda function that inspects the request body and identifies a file to be uploaded to a S3 packet. If the upload operation stores the file in a specific folder, then another Lambda function is executed. This processes the user-provided information, which is included in an email notification sent via the Amazon SNS service. Our approach to statically analyzing serverless applications combines information extracted from the infrastructure and the application code. This is necessary because the infrastructure code specifies permissions, events, and handlers related parameters. These can be used to instrument the application code and obtain a synchronous-like program execution flow. The key advantage of this approach is that the instrumented code can be analyzed with a general-purpose static analysis tool. Our prototype was implemented as a Python command line utility which semi-automatically modifies the code under test. The instrumented code is then analyzed with PISA. For those who are not familiar with it, PISA is an open source tool developed by Facebook and that supports interprocedural data flow analysis of Python code. The test performed with our micro-benchmarks show that our analysis tool is able to detect the expected data flows in 7 cases out of 10. As for the others, we have 2 false positives and 1 false negative. The details are in the paper. I will only say that the false positives are caused by limitations of our current prototype, which we intend to address in the future. Now, another question you might have is this: how can you extract information from the application code to support the instrumentation step? The answer is we use the abstract syntax tree. Let's take a look at a couple of examples. They are very simple but show some of the key ideas of our approach. Before we start, don't forget that this is a research code, so it will not be polished to perfection. I would also emphasize that all the examples rely on the AST module, which is a part of the Python standard library. The first example is this. We want to extract all the names of the functions defined in a given source code file. This can be achieved in 2 steps. First, we create an in-memory data structure containing the AST by calling ast.parse, and then we traverse the tree with ast.walk. All we need to know is that function definitions are instances of the class function def, and that the property name stores the name of the function. And what if we had to extract all the classes defined in a given source code file? The approach would be exactly the same, but when traversing the abstract syntax tree, we would need to identify instances of the class and the class def. And how about extracting something a little bit more interesting than just functions and classes? For example, type annotations. Let's take a look at the source code on the top left corner. It contains several variable initializations, but not all of them include a type annotation. Can we use the AST to identify all the variables that are initialized with a type annotation? The answer is yes, and the approach has not changed. This time, we need to identify AST nodes that are instances of the class annotated aside. In this case, the code also includes an exception handler because depending upon the specific type annotation, the information we'll be looking for will be stored in a different property. Last example. At the very beginning, we saw how to process AST nodes with function definitions and to extract the names of the functions. How about processing actual function calls? Let's take a look at the source code on the top left corner. 2 simple functions are defined, but only function 1 can be called with arguments that are either all strings or integers. Can we identify the calls to function 1 and differentiate them on the basis of the input arguments type? The answer is, once again, yes, and the approach is always the same. This time the class we are interested in is ast.call, and what we have to do is to inspect the args property of the filtered nodes. I would highlight that we can also extract the source code line where the processor function call is, because there is a property that stores this information. Before concluding this presentation, let me emphasize that all the AST and processing examples we've been looking at are focused on the extraction of information from the source code. To achieve this, as I explained before, we simply have to traverse the abstract syntax tree. But how about modifying the source code? This is exactly what we need to instrument the application code. In a nutshell, this is what we do. We combine the information extracted from the AST with the infrastructure code, and then we modify the original AST by adding new synthesized AST nodes. This is what we call code synthesis and injection, which is the key step to instrumenting the code under test. So, what are the key takeaways of our study? We've been working on a new approach to statically identifying data flows that can lead to code injection and information leakage in serverless applications. To evaluate our approach, we have designed a new suite of micro benchmarks, and the test conducted with these show that the proposed approach is feasible. I emphasize that this is ongoing research, so stay tuned if you want to know more. In the meantime, you can scan the QR code for more information on our work, and if you have any questions, please don't hesitate to get in touch. Thank you very much for listening.